study an analog of algebraic geometry of a structure that is not a field, in this case, the tropical semiring. And the aim of today's part is to showcase what are the relationships between the tropical geometry and the classical algebraic geometry. Okay. So, in order to go to this second part of the lecture, we will need some definitions, right? So let me recall the definitions from yesterday. So we started with the definition of the tropical semiring, right? And we said that the tropical semiring has two variants, which are actually isomorphic. And when you do tropical geometry, you can just use your preferred variant of this tropical semiring. So there is the max plus version and the min plus version. And in this max plus version, well, we have a semiring, which is like a ring, but you cannot do subtraction. And in the semiring, we have two operations that we call addition and multiplication. And the addition is the maximum of two numbers, and the multiplication is the classical addition of two numbers, right? So in this way, in this max plus semiring, we have 2 plus 3 is 3 because it's the maximum, and we have 2 times 3 is 5 because that's the addition. And in my presentation, I will use the max plus semiring. Okay, so that's the max plus semiring. And then we said that if we want to do some algebraic geometry, we need the notion of a polynomial. Right? So that was the definition of a tropical polynomial. So what is a tropical polynomial? Well, it's an expression of this form. So it's like a classical polynomial, except for the fact that I replaced the classical operation, addition and multiplication, by the tropical operation. So this is maximum, and this is addition. And then we discussed the fact that, well, if you have such a formal expression, then as for a usual polynomial, you can evaluate this as a function. Right? So with a tropical polynomial, I have the associated tropical polynomial function, which simply comes by interpreting these operations in the standard way. Right? So if I interpret this as maximum and this thing as addition, so like exponentiation is now multiplication, and this is addition, then I get that the evaluation of this polynomial is this function. So it's the maximum of a bunch of affine functions. And so is this okay so far? Okay, so the tropical polynomial is a maximum of a bunch of affine functions. So in particular, it is like piecewise affine, right? And we spent the last lecture basically by giving some examples of these functions. And then we discussed the structure of this piecewise affine pieces, right? So we said that this tropical polynomial, in fact, splits the space into polyhedra. On each polyhedron, the function is affine. And this polyhedra have a nice structure of a polyhedral complex. So then we discussed about polyhedral complexes, and we finished by this theorem that basically claimed that there's the compositions of space are in a very nice duality with the regular subdivisions of Newton polytops. However, for this lecture, we will not need this. For this part, okay, so that I will also skip. So in this part of the lecture, we are going to showcase some relationships between tropical geometry and classical algebraic geometry. Okay, so to start, we should define what is a root of a tropical polynomial, right? Because we are interested in zeros of polynomials in classical algebraic geometry. So let us try to define a root of a tropical polynomial. Okay, so let me recall again that a tropical polynomial is a maximum of affine functions. So it is not so clear how to define what it means for this thing to like achieve zero, right? So we said that in the tropical semiring, the neutral element of addition is minus infinity, right? However, this function, well, it's never equal to minus infinity. So in some sense, this function doesn't have roots in the tropical semiring, right? So we need some sort of a different definition of a hypersurface. So here is the definition of the tropical hypersurface, which may seem very counterintuitive at first, but then we will motivate why this definition is good. So the definition is as follows. So the tropical hypersurface of a tropical polynomial is the set of all points x such that the maximum is the expression is achieved by at least two terms. Okay, so that's just the definition. So for most points, right, this maximum is achieved by a single term, right? If I take a generic point, the maximum is achieved by a single term. So I take by my tropical hypersurface is the points for which there are at least two terms. And then there is a simple proposition saying that, well, a tropical hypersurface can be equivalently defined as these three things. So for those of you who weren't there here yesterday, so this notation is about this cell decompositions of the space, right? So we said that the space is decomposed in many cells. Some of them are full dimensional, some have lower dimension. So this hypersurface is the union of all lower dimensional cells. But you can also think about this hypersurface using this third bullet, which doesn't require the previous lecture. So the tropical hypersurface is the set of all points on which this function is not differentiable. Right?
I missed the last lecture, I'm sorry, but there's two things I'm confused about here. What does it mean to differentiate a tropical polynomial?
Okay, so this is just a ring function, right? So you think about this function as just like a normal function, right? It's a function that to x associates the max of this. So we can differentiate this function like in the real analysis. And on almost all points, it is differentiable. However, if you have like the points at which the maximum is achieved by two terms, then this is the place where it stops being differentiable, right? Because you can have like an absolute value thing. So it's differentiable for all x is smaller than 1, differentiable for all x is greater than 1, but it's not differentiable at 0. So this is a generalization of this observation.
And your second bullet is saying that you could never have a C of I of dimension n-2.
Yeah, I can. Yeah, but the CIs are just defined in such a way that they, yes, so these cells are embedded one in another. So this cell contains a lot of cells of lower dimension.
Cells, I see. Okay.
Yeah.
So that's
So this is why it's true. So if you take the guys on the dimension n-1, they will already cover everybody of lower dimension.
I'm still trying to wrap my head around the differentiable.
Okay, so let me show you this on this example. Okay.
That would be great.
Okay, so okay, let me go here. Okay, so here is a univariate tropical polynomial. So this is a maximum of 3 affine functions, right? So this is this function that I drew here. Okay. So now, if x is sufficiently small, then the maximum is 0. Right? And then we said that in between this interval, the maximum is 2 plus x. And on this interval, the maximum is minus 2 plus 3x. Okay. So now on this interval, open interval is open, it's differentiable. On this open interval, it's differentiable. And on this open interval, it is differentiable, right? However, it's not differentiable precisely at this point and at this point. And what's the definition of the tropical hypersurface? Well, it's a point at which the maximum is achieved by 2 terms. So here it's the first 2 terms, and here is the last 2 terms. Okay. So this is why these two things are equivalent. Okay. Right. So here I have the a more complicated example, right? So this is a bivariate tropical polynomial this time that I have shown also yesterday. So here we have, I think, 8 monomials. So what happens here? Well, in this example, there are points on which each of these 8 monomials is the only one that dominates. right? So here I have these 8 full-dimensional regions, and on these 8 full-dimensional regions, exactly one term achieves the maximum, and on these full-dimensional regions, the function is differentiable, and we have this bold part, and on this bold part, there are at least 2 terms that achieve the maximum, and these are precisely the points on which the function is not differentiable. And now I claim that this merits to be called a hypersurface. So now let me try to convince you why this thing merits to be called a hypersurface. So in order to do that, we will introduce a field that is very commonly used in tropical geometry, which is the field of Piso series. So there's actually a lot of fields that you can use in order to do tropical geometry, but this is the most popular one. Okay, so we want to claim that tropical hypersurfaces will be related to the usual hypersurfaces over non-Archimedean fields. And this will be an example of a non-Archimedean field, which is called the field of Piso series. And so Piso series are formal series with real exponents, okay? Sorry, with rational exponents. So a Piso series is a formal series of this given by such an expression. So here t is my formal parameter. And now these exponents are given like this. So the ai are integers, so they can be negative. And n is the common denominator of my series, right? So these are basically series with rational exponents, but somehow the denominator is the same for every term, right? And now the coefficients. So the coefficients here are supposed to be complex numbers. And I will denote this set of Piso series vector. So now what can you do with such a series? Well, you can add such series, and you can also multiply such series in the standard way, right? So you add them term by term. So you know now the denominator of your new series is the common denominator of the previous ones, right? You may need to multiply the denominator. And you can also multiply such series just by taking the Cauchy product, right? And again, you have to adjust the denominator. So what is the somehow the good property of this set? Well, is that with these 2 operations, this forms an algebraically closed field. Okay, so if you just take series with natural exponents like Taylor series, then this is not even a field, right? If you go to series with integer exponents, maybe negative, then this set of Laurent series forms a field, right? But it's definitely not algebraically closed. And if you allow your exponents to be of this form, then now you have an algebraically closed field, right? Okay, and I forgot to say that the sequence is supposed to be increasing, but this is like in the usual Taylor series, right? It's supposed to be 0, 1, 2, blah, blah. In Laurent series, it's supposed to be -5, -4, -3, blah, blah. And here it is also supposed to be increasing, but with the same. Okay. So by taking more general exponents, I made this into an algebraic.
So what's the secret to making it algebraically?
So well, basically, so like the first thing is that, well, you need to have roots like x to the n minus t is supposed to have a solution, right? So this is why you need this kind of an exponent. And now, if you want to say why this is algebraically closed, well, I guess there are many proofs. I like the proofs that use the fact that these fields are Henselian. And then you can prove that this field is Henselian basically by hand. So if it has like a simple root of an initial form, then you can say, well, here is an algorithm that will produce mirror. So yes, but this kind of a proof requires you to know that if it's Henselian, then it's like algebraically closed. It's not so easy to have like a proof totally by hand, I think. Okay. Okay, so what's the difference between such an algebraically closed field and real numbers? Well, this field is non-Archimedean, meaning that it is equipped with a non-Archimedean valuation map. So what's the valuation of a piece of series? So the valuation of a piece of series is its smallest exponent. So here I have a series of this form, and my evaluation will be this smallest exponent. With the convention that the valuation of 0 is plus infinity. So how can you interpret this? So imagine that this series is convergent for small t. Then this valuation tells you what is the behavior of your series around 0, right? Because around 0, this term is the most important term. Okay, so it says roughly that this function around 0 behaves like this term, at least in terms of the rate of growth. Okay, and the second property here is that this valuation function, well, it goes into rational numbers with plus infinity, right? Because A0 over M is rational. Okay, and now we have the two properties that relate this to tropical algebra. So the valuation has the following two properties. So this maybe is the easier property. So if I take the valuation of a product of two series, then this is precisely the sum of the two valuations. So why is that? Well, how do I define the product? Well, it's a Cauchy product. So if I have a series of the form t to the power 3, multiplied by a series that starts with t to the power 5, I will get series that starts with t to the 8. And now is the second property that if you add two series together, then it's at least the minimum between the valuations. And now we have to distinguish two cases, right? So if I add a series that starts with T2 to a series that starts with T, so in my sum, I will start with T2 as the smallest one. But there is a catch that if I add a series that starts by T to the power 2, and I add a series by minus T to the power 2, then what happens when I add them together? Well, maybe the leading term cancels, and I get a series of a strictly smaller valuation. Right? So this is just an inequality, and it can be strict if it so happens that the leading terms cancel. But that's the only case where it's strict enough. And now this relates to the tropical algebra, because it somehow tells us that the valuation turns addition into minimization and multiplication into addition. So we see the operations from the min plus semi-ring. However, in this talk, I made my slides in the max plus semi-ring. So if I want to have a max plus operation, I will lose the negation of the valuation, okay? So this is my negated valuation map. So my negated valuation map, it goes from the Piso series to rational numbers with minus infinity, and it satisfies these two properties of the max plus semi-ring. So the valuation, negated valuation of the product is the sum of the negated valuations, and the negated valuation of the sum is at most the maximum of the two. Is this fine? This one. This one, yes, I think. Okay. So now we can try to relate this to the study of tropical polynomials, right? So how can we relate a polynomial over Piso series with a tropical polynomial? So we will just relate them by, let's say, brutally tropicalizing the polynomial. So we get a polynomial over Piso series, given like this. So we will define the formal tropicalization of this polynomial, and that will be a tropical polynomial. So how do I define it? Well, I just take the same set of exponents. But as my coefficients, I will just take the coefficients that I have here, and I will apply my valuation. Negative.
By polynomial Jesus series, you mean that each x,
each C alpha,
each C alpha is a
each C alpha is a piso series. The coefficients are, yes, the coefficients are piso series. Okay. So it's a polynomial whose coefficients are piso series. So each of these coefficients has some valuation, and I will just apply this valuation, and I get a new thing, and I will interpret this new thing as a tropical polynomial. Okay. So let us do an example. So here is an example. So let us look at this affine polynomial. Right? So now the two coefficients are piso series. So compute the valuation of the line of this polynomial and compare it with the tropical hypersurface. Okay, right. So as you can see, I will only compute the valuation of the line that on the non-zero for simplicity. Okay, so let us try to do it. So how could we start computing the valuation of this line?
Can you go back to the last slide for a second?
Sure.
Okay.
Okay. Okay. So like the first part is like not related to tropicalization, right? For now. So it's just you have a line over a piso series, and you want to compute its valuation. It's imaged by this val function, right? And then the second part asks you to see what happened in the by tropicalization. Okay. So in this simple example, right, this line, p of x equals 0, well, we can just, reparameterize it, right? So this line has this parametric description, right? If you give me x1, I can just split you x2. Okay? So now let us look what happens to valuation. So imagine that the valuation of x1 is greater than -1. And what will happen in this expression? Well, this thing will have valuation greater than 2. So when I add this thing, the valuation 2. Yeah, do you agree? So for valuation greater than -1, we get that the valuation of x2 is 2. Okay, so what happens if the valuation is strictly smaller than -1? Well, then this thing will have valuation strictly smaller than 2, and this has valuation 2. So after I add them, it will be this, the valuation of this thing that will dominate the C. So I will have this relationship. Do we agree? Okay. So now there is only one case missing. So what happens if the valuation of x1 is exactly -1? Well, in this case, I can have some cancellation between these two terms. So if I take, for instance, this x1 is t to -1 plus t to -1 plus 1p, or negative p. And this is exactly the moment where I have a cancellation, right? T to the 3 times x1 will be t minus 2 plus t to minus t to 2 plus t to 2 plus this term, right? So we get that the valuation of x2 can be any rational number not smaller than by modifying it. Okay. So what is the conclusion of this exercise? Okay, so here I will pass to negative valuation. So the negated valuation is certainly included in the union of three half-lines. So that's the first half-line, x1 smaller than 1, x2 equals to -1. That's the line coming from this first case. So we are certainly, for a valuation of x greater than -1, we are on this half-line. So that's the half-line coming from the second case. Like if valuation is smaller than -1, then we are certainly on this line. And that's the half-line coming from the third case. If the valuation is -1, then we will be on this half-line. Okay, and you can convince yourself that any rational point in the union of these three half-lines belongs to the valuation. So here, if I want to have x1, let's say x1 0 and x2 equals -2, I will just take t to the power 0 here, and I will get some x whose valuation will be on this half. So now we can draw the valuation. So if we draw the valuation, so these are the three half-lines. That's the first half-line. That's the second half-line, and that's the third half-line. Okay. And now, if you recall, this looks very similarly to linear tropical polynomials that we have seen yesterday. So more precisely, the formal tropicalization of this polynomial, let me just recall you the polynomial. So this is t1 minus t plus t to -2. So when I do the negated valuations, I get 0, -1, and 2 as my valuation. So these are the negative valuations, 0, -1, and 2. And if you look at the tropical hypersurface of this tropical polynomial, you get exactly the same picture. So in this example, we convince ourselves that the valuation of this affine line is exactly the set of rational points on the associated tropical hypersurface. Is this clear? Are there any questions, doubts? Example fine? So if the example is fine, then we can say, well, actually, this example is an example of a theorem. So this is one of the first results in, let's say, the modern tropical geometry, is that this holds for any hypersurface. So if you have a polynomial, this is known as the Kaplan theorem. So if you have any polynomial of a piso series, then the negated valuation of the associated hypersurface coincides with the set of rational points on the tropical hypersurface that we get by tropicalization. And moreover, this set of rational points is a dense subset of this tropical hypersurface. So in other words, the theorem tells us that tropical hypersurfaces are exactly the valuations of classical hypersurfaces. Okay? And this is why we claim that our definition of a tropical hypersurface is like a good definition, right? Because it is really a hypersurface. It is a valuation of a classical hypersurface. Good. So I have few slides where I try to give some proof of this theorem. So let us see if we can at least understand the easy direction, right? So the easy inclusion. So let us take a polynomial over piso series and let us look at this formal tropicalization, right? And let us imagine that I have a 0 of this polynomial. I have x such that p of x is equal to 0. Then what happens? Well, here I have a sum of some piso series. Right? And the sum of piso series happens to be 0. So what does it mean? Well, it means that every term had to cancel. if the sum is 0. So in particular, there are at least 2 terms that have the smallest valuation. Right? Because if I have a single term here with the smallest valuation, then it cannot cancel with anybody in any way. So I have to have at least 2 in order to achieve cancellation. But what does it mean that I have at least 2 terms that achieve the same valuation? Well, if I apply my valuation map just to this term, then the valuation is exact because it's got multiplications here. So the valuation is precisely this thing. So we get that the valuation of my point must be on the tropical hypersurface. Right? The valuation must satisfy the property that there are at least 2 terms that achieve it. So that's the easy conclusion, right? And now the complicated part is to convince ourselves that the opposite is true. If you give me a point on the tropical hypersurface, then I can find a corresponding point in the algebraic hypersurface whose valuation is my point on the tropicals. Okay. So in order to do that, well, there's a simple definition. Given x in R, we will say that the point on of our Piso series is a lift of x is the valuation of x of both x's. Okay. And now the point of proving the opposite inclusion is to say, well, if I take x on my tropical hypersurface, I can find the lift of x that is on the algebraic hypersurface. So the proof here starts with a small lemma, saying that if I have any x and any sufficiently generic lift, old x, then tropicalization commutes with valuation. Right? So the valuation of P of x is the same as the tropical polynomial of the valuation. So this is not true for any point and any lift, for any lift of x, but this is true for a sufficiently generic lift. And here is the proof. So, okay, I took x in Rn, so let me take some lift, right? So I will only take very simple lifts. So I will take t to the power xi, and I will multiply them by wi, where w are complex. So I will only look at Piso series that have single term. Okay, so let me look at such a tuple. Then when I evaluate my polynomial on such a tuple, I get an expression of this form. And now I hope that it's somewhat clear that if my tuple of complex numbers is sufficiently generic, then in this expression, I cannot have a cancellation of, well, I cannot have cancellation of any terms, to be honest, if this is sufficiently generic. So in particular, the leading terms in the monomials cannot cancel. So since leading terms cannot cancel, so the valuation of the entire thing is the negated valuation is the maximum of the valuations, right? So in general, here is the inequality that can be strict, but if my point was chosen to be sufficiently generic, then this will be equality. I will never achieve a strict inequality. Is that fine? Okay. And now we can prove this Kapranov theorem at least for one variable. So we do a univariate proof, and already the univariate proof is a very mysterious thing. Okay, so let us suppose that my polynomial is univariate. So I told you that the field is algebraically closed, so I can decompose my polynomial in this way. So since I have now this nice decomposition, I can, let's say, naively or formally apply tropicalization to this expression, right? So if I do that, I get this function that I obtain just by naively replacing everything with tropical operations. Okay, and now here's my claim. So now fix some point in R. Then for any sufficiently generic lift, what is going to happen? So by our previous lemma, the tropical polynomial evaluated at x is the same as the negated valuation of g of x, right? So that's the previous step. But by this argument, if my lift is sufficiently generic, I will not have any cancellation here in this terms. So by the same argument, this thing will be also equal to this function f. So now I see that this tropical polynomial function and this function f is actually the same function. Even though this doesn't come from, like this depends on expressing p in the monomial basis, while this comes from some other expression. So these are two different things, but as functions, then they coincide. And now you just have to check that this function is not differentiable precisely on this point, because here the maximum will be the maximum in this expression will be achieved twice. So that's an easy exercise from linear analysis that this is exactly the point of non-differentiability. So it means that the tropical hypersurface is exactly what. Okay, so I find this proof to be very, very nice, but also a little bit tricky, right? It doesn't really tell you why this is true, right? It's just a trick that says you, okay, it's true. But okay, yeah, it uses the fact that it's algebraic, so maybe that's the reason. So let me leave this with an exercise for you. So prove the case of multivariate polynomials by reducing it to the univariate case. Okay. So you can think about how to prove this. Okay, so now we have the first theorem that the tropicalization of a hypersurface is a tropical hypersurface, right? So the valuation of hypersurface, tropical hypersurface. And this tropical hypersurface can be nicely described just by taking a polynomial and applying the valuation to the coefficients. Okay, so now let us try to generalize this theorem. So now let us take two polynomials. And okay, let us take two affine polynomials for simplicity. So now consider the affine space defined by this. So what can we say about its valuation and about the intersection of the associated tropical hypersurface? Okay, so now this is a very simple affine space. So what is this? It's a single point, right? So this is a single point, and this point is minus 3, 5. So what is the valuation? Well, it's 0, 0. That's a series of valuation 0. That's a series of valuations 0, 0. However, what can we say about the tropical hypersurfaces or the tropical polynomials? Well, everything here has valuation 0, right? So this is 0, 0, and 0. And this is 0, 0, and 0. Right? So the tropical polynomials of this guy and this guy is actually the same tropical polynomial. This thing. And the tropical hypersurface of this thing is precisely the union of three lines, half lines, that we have seen before, right? So now we see that the naive version of this theorem fails like completely. So here I have a single point, and by intersecting the tropical hypersurfaces, I got three half lines. Right? So that's
The sum of the squares.
sorry?
You can take the sum of the squares and make it 0.
Yes, so now the question is, can we somehow find a solution to this? And indeed, there is a way. So that's the second theorem, is how can we compute the valuation of something more complicated? How can we compute the valuation of a variety? Right. So in order to do that, we will need to take bigger intersections. Okay. So now we will take a variety. So we will start with an ideal, right? And we will let V of I be the associated variety in the terms. Okay. And as you can see on the slide, I took an ideal not really over the polynomials, but over the Laurent polynomials. So my long polynomials are allowed to have negative exponents. But this is mostly for convenience. It's easier to do proofs in this setting. If you want to work only with ideals over the polynomial ring, then that's fine. There is like some modification that will need to be done later. Okay. So this will be my variety, right? I have an ideal, and I look at all of the polynomials that, all of the points on which all of the polynomials are 0 for this ideal, so that will be my variety. And now I will just define the valuation of the string to be the tropical variety. And that's the definition that we use. Okay, the valuation of a variety is called tropical variety. So now here is the theorem that has the name of fundamental theorem of tropical geometry. So the theorem claims that the tropical variety of an ideal coincides with the intersection of negated valuations of all hypersurfaces in my ideal. Okay, so like let me just try to unpack this notation, right? So here I have a large collection of polynomials in the ideal. I tropicalize every single of these polynomials. I take the tropical hypersurfaces of every single of these polynomials. I intersect all of them, and that will give me the tropical variety. Okay. So I need to take a much bigger intersection. And there is the second part of this theorem saying that actually there exists a finite set of polynomials that I can choose. So from the ideal, you can extract some finite set such that if you take tropical hypersurfaces from this finite set, you will recover your tropical variety. Okay. Is this fine? Okay, good. So now let me give you another description that is a little bit technical, but very useful for computations. So this description uses the notion of a leading coefficient of a Piso series. So we have seen that valuation is the leading exponent, but you also have the leading coefficient. This guy here. Okay? So now there is this definition, this complicated looking definition, that if you have a polynomial, let's say the Laurent polynomial over Piso series, and a point in Rn, we can define what is the initial form of my polynomial at the point. And that now will be a polynomial at over complex numbers, right? So I will go from a polynomial over Piso series to a polynomial over complex numbers. And what is this initial form? Well, so the initial form is defined a little bit like this. So if I fix a point W, which you can think as a point in the tropical space, then at this point, well, there are only let's say the most interesting monomials of my polynomial key are the ones that achieve the lowest valuation. So these are, let's say, the dominating terms in this expression. Okay, so I will only look at these monomials which achieve the minimum of valuation. Okay, and then what I will do is I will multiply them by this factor so that everybody has valuation 0. Every coefficient has now valuation 0, and I will take the leading terms. Okay, so that may seem a little bit like a complicated definition, but the point of this definition is that it satisfies the following, right? So if I have a point x at which my polynomial is 0, then the leading terms have to cancel, right? So what does it mean that the leading terms have to cancel? Well, it means exactly that this polynomial has to cancel when I evaluate them on the leading coefficient of x. Is this understandable? Right? Maybe it's a bit complicated as a definition, but the idea is okay. You know, if you want P of x to be 0, then at least the leading terms have to add up to 0, and then you say, okay, so which terms will be the leading terms? And then when you write this definition, you will realize that actually it means that there is this polynomial over complex numbers that has to cancel on the leading coefficient. Okay, so you can introduce such a polynomial over complex numbers. And now with this polynomial, well, we have this very simple proposition, which is just the definition, that the point is in the tropical hypersurface if and only if this initial format W is not a monomial. And this is generalized to tropical varieties as follows. And this is a kind of a nice definition that I wanted to show you, is that if you have an ideal over this Laurent polynomials and the point W, then you can define what is known as the initial ideal of your ideal. So you take all of the initial forms. So now there are polynomials over complex numbers, and you look at the ideal generated by them. So now you get an ideal over complex numbers.
I just went wrong with my intuition. So the classical algebraic geometry, when you take initial ideal, you end up with a monomial ideal. And here you're saying,
yes.
So
what do you end up with?
So there's this whole business in regular algebraic geometry where people take initial ideals.
Yeah.
And it's sort of, to destroy your variety and make it make it define intersections of linear spaces. And here, but that means all the generators of the ideal are monomials. But now you want the initial thing of P is not a monomial. That's just kind of causing these psychological disorders.
Yeah, but these points are not generic in any way, right? These points W on which this will be a monomial.
So when you refer to an initial ideal for a monomial ordering, where you can select the leading.
Exactly.
But here it's for a weight. So it's like you take the degree of.
I see.
Or you may have several.
I think.
Yeah.
I got it. Yeah.
Okay.
So how much time do you need? Maybe 10
Oh,
minutes?
yes, we
have 10 minutes or more.
yeah, I think Lynn asked me to finish like in 5. Is this fine or okay? Because this is basically the point where we can somehow try to wrap things up. I will just show an example, please. Okay, so yes, the basic idea is that you have an ideal of a Piso series, and now for every real point, you can associate to it an ideal over complex numbers. And now the tropical variety of I coincides with the set of W such that this initial ideal is not unit. Well, in the Laurent case, and if you are in the polynomial case, then you have to replace this by this initial ideal doesn't contain a monomial. Okay, so this is another way of defining a tropical variety, and this is the way that people use in computation because ideals over complex numbers is something a bit more familiar. Okay, so I will finish this by giving you just somehow I wanted to give you some sort of an explanation for our previous example, right? So in our previous example, we have seen an example of a linear space that when I tropicalize the equations naively, I don't get the tropicalization, right? However, the theorem guarantees me that there is some finite set for which I can achieve the good tropicalization. So, and it turns out that these finite sets for linear spaces have a particularly nice interpretation. Namely, you can just take the so-called circuits. So circuits are some sort of special vectors. And so circuit is a vector of a linear space with minimal support. So it is a vector that has let's say, a maximal number of zeros as coefficients. Okay, so let me just skip this and just tell you that, well, in our example from before, you know, you have these two equations, and now we want to somehow compute the circuits in the space spanned by these equations. So here are the two equations, and now if we want to find combinations that have like maximum number of zeros, then the maximum number of zeros you can have is 1. So you can have a 0 here, you can have a 0 here, or you can have a 0 here, right? So now I replace these two equations by 3 equations, which are in this ideal. And I will get these 3 tropical polynomials, which are different than the tropical polynomials I got before. And now after I intersect these 3 tropical polynomials, I will get a single point, as expected. Okay, so let me finish here, and let me just say that if you want some more content, then there is a few more slides about amoebas, logarithmic limits, and so on. Thank you.